The universe is vast and full of mystery. Among its many wonders are planets beyond our solar system, known as exoplanets. These celestial bodies orbiting distant stars hold the potential to answer one of humanity's oldest questions. Are we alone? In this quest for cosmic companionship, one exoplanet in particular has captured our imagination: Kepler-22b. Kepler-22b is a super-Earth, a planet larger than Earth but smaller than Neptune. It orbits a star much like our Sun, raising intriguing possibilities. Could this distant world harbor life? The answer to this question remains a tantalizing mystery, but Kepler-22b's discovery has ignited our collective curiosity, pushing us to explore the cosmos like never before. The discovery of Kepler-22b marks a pivotal moment in our understanding of the universe. It provides a glimpse into the diversity of planetary systems beyond our own. As we delve deeper into the study of exoplanets, each new discovery brings us closer to unraveling the secrets of the cosmos and our place within it. Finding exoplanets is no easy feat. These celestial objects are incredibly distant and faint, often dwarfed by the brilliance of their host stars. Imagine trying to spot a firefly next to a spotlight, and you begin to grasp the challenge faced by astronomers. To overcome this obstacle, scientists have developed ingenious methods for detecting exoplanets. One such method is the transit method, which relies on observing the subtle dimming of a star's light as an orbiting planet passes in front of it. This dimming, though minuscule, provides a telltale sign of the planet's presence. The transit method, while effective, requires incredible precision and sensitivity. Even the slightest variation in a star's light, unrelated to a planet, can throw off the measurements. Despite these challenges, the search for exoplanets continues, driven by the profound implications of finding another world like our own. Enter the Kepler Space Telescope, a marvel of engineering launched in 2009 with a singular mission to find Earth-sized planets orbiting other stars. Kepler's gaze was fixed on a specific region of the Milky Way, continuously monitoring the brightness of over 150,000 stars. The telescope's sensitive instruments were designed to detect the faintest dips in starlight, signaling the presence of an exoplanet transiting its host star. Kepler's data revolutionized our understanding of exoplanets, revealing that they are not the exception, but rather the rule in our galaxy. Among Kepler's many discoveries, Kepler-22b stands out as a particularly intriguing find. Located approximately 600 light-years from Earth, this super-Earth orbits its star within the habitable zone, the region where temperatures are just right for liquid water to exist on the surface. This tantalizing possibility has propelled Kepler-22b to the forefront of exoplanet research. Kepler-22b's discovery is a testament to human ingenuity and our insatiable thirst for knowledge. It represents a significant step forward in the search for life beyond Earth, offering a glimmer of hope that we are not alone in the vast expanse of the cosmos. While much about Kepler-22b remains unknown, its presence fuels our imagination and inspires us to push the boundaries of scientific exploration. The quest to unravel the mysteries of this distant world will undoubtedly lead to new discoveries and a deeper understanding of our place in the universe. In the grand tapestry of the cosmos, Kepler-22b is but a single thread, yet it holds the potential to reveal profound truths about the nature of life itself. As we continue to explore the universe, we do so with a renewed sense of wonder, driven by the belief that somewhere out there, among the billions and billions of stars, another Earth awaits our discovery. Imagine a telescope so powerful it can detect the faintest flicker of a candle from thousands of miles away. Now picture that telescope hurtling through space, its unwavering gaze fixed on a distant patch of the Milky Way. This was the Kepler Space Telescope, a marvel of modern engineering designed to hunt for planets beyond our solar system. Kepler's mission was ambitious: to continuously monitor the brightness of over 150,000 stars, searching for the telltale signs of orbiting planets. The telescope's sensitive instruments were trained on a specific region of the constellation Cygnus, a star-rich area thought to hold the potential for harboring Earth-like worlds. Day and night, Kepler diligently collected data, its unblinking eye capturing the subtle variations in starlight that could betray the presence of an exoplanet. The sheer volume of information gathered was staggering, requiring sophisticated algorithms and the tireless efforts of scientists around the world to analyze. Kepler's primary method for detecting exoplanets was the transit method, a technique that relies on observing the dimming of a star's light as a planet passes in front of it. Imagine a moth fluttering across the beam of a powerful searchlight. The moth itself may be invisible, but its shadow reveals its presence. Similarly, when an exoplanet transits its host star, it blocks a tiny fraction of the star's light, causing a slight dip in its brightness. This dip, though minuscule, is detectable by Kepler's sensitive instruments. By carefully measuring the duration and depth of the dip, scientists can infer the size and orbital period of the exoplanet. The transit method, while effective, has its limitations. For a transit to be observed, the exoplanet's orbit must be aligned edge-on to Earth. Otherwise, the planet will pass above or below the star from our perspective, and its transit will be missed. This means that only a small fraction of exoplanets are detectable using this method. In 2009, amidst the vast sea of data streaming back from Kepler, a faint signal caught the attention of scientists. It was a subtle dip in the light curve of a star designated Kepler-22, located approximately 600 light-years from Earth. The dip was minuscule, a mere fraction of a percent, but it occurred with a regularity that hinted at something extraordinary. Every 290 days, like clockwork, the star's light would dim for a brief period, suggesting that an unseen object was orbiting it. The duration and depth of the dip indicated that the object was roughly twice the size of Earth and orbiting its star within the habitable zone, the region where temperatures are suitable for liquid water to exist on the surface. Excitement rippled through the scientific community. Could this be the long-sought-after Earth-like planet, a world capable of supporting life as we know it? The possibility was tantalizing, but further observations were needed to confirm the existence of Kepler-22b and unravel its secrets. Confirming the existence of an exoplanet is a rigorous process requiring multiple observations and independent verification. In the case of Kepler-22b, scientists had to rule out other possible explanations for the observed dips in starlight, such as instrument errors or the presence of background stars. To confirm Kepler-22b's existence, astronomers turned to ground-based telescopes using a technique called radial velocity measurements. This method detects the wobble of a star caused by the gravitational pull of an orbiting planet. The wobble, though incredibly small, can be measured by observing the Doppler shift of the star's light. The radial velocity measurements confirmed Kepler's findings, providing independent evidence for the existence of Kepler-22b. The data revealed that the planet has a mass approximately 2.4 times that of Earth, making it a super-Earth. With its size, orbit, and host star similar to our own, Kepler-22b quickly became a prime candidate for further study. The discovery of Kepler-22b sent shockwaves through the scientific community and captured the imagination of the public. Here was a planet, albeit a distant one, that shared some striking similarities with our own. Could this be a sign that we are not alone in the vast expanse of the cosmos? Kepler-22b became a symbol of hope, a beacon in the darkness, reminding us that the universe is full of possibilities. Its discovery fueled our collective desire to explore the cosmos, to seek out other worlds, and to answer the age-old question, are we alone? While much about Kepler-22b remains shrouded in mystery, its discovery marked a pivotal moment in the search for life beyond Earth. It showed us that planets like our own, orbiting stars like our Sun, are not a cosmic anomaly, but rather a common occurrence in the Milky Way. The quest to unravel Kepler-22b's secrets had just begun, and with it, a new chapter in our understanding of the universe and our place within it. Determining the size and mass of an exoplanet like Kepler-22b, located hundreds of light-years away, is no easy feat. Astronomers rely on a combination of ingenious techniques and meticulous observations to glean information about these distant worlds. One crucial piece of information is the planet's radius or size. This can be estimated by analyzing the amount of starlight blocked during a transit. The larger the planet, the more light it will obscure as it passes in front of its star. In the case of Kepler-22b, the transit data revealed a radius approximately 2.4 times that of Earth, classifying it as a super-Earth. Determining the mass of an exoplanet is more challenging. One method, known as the radial velocity method, measures the wobble of a star caused by the gravitational tug of an orbiting planet. The more massive the planet, the stronger its gravitational influence, and the more pronounced the star's wobble. By carefully analyzing the star's light spectrum, astronomers can detect these minute wobbles and calculate the planet's mass. For Kepler-22b, the radial velocity measurements suggest a mass somewhere between that of Earth and Neptune. Section 2, a year on Kepler-22b. Kepler-22b completes one orbit around its host star, Kepler-22, in approximately 290 Earth days. This orbital period, shorter than our own year, offers tantalizing clues about the potential seasons and climate on this distant world. Unlike Earth, whose seasons are primarily driven by the tilt of its axis, Kepler-22b's seasons, if any, would be influenced by its orbital eccentricity and proximity to its star. If its orbit is significantly elliptical, Kepler-22b would experience varying distances from its star throughout its year, leading to potentially dramatic temperature swings. However, if Kepler-22b's orbit is more circular, as some data suggests, its seasons would be more moderate, with less pronounced temperature variations. The exact nature of Kepler-22b's seasons remains a mystery, waiting to be unraveled by future observations and more detailed climate models. Section 3, the habitable zone. Not too hot, not too cold. The habitable zone, also known as the Goldilocks zone, is the region around a star where temperatures are just right for liquid water to exist on the surface of a planet. This region is crucial for life as we know it, as water is considered an essential ingredient for life's emergence and evolution. The location and width of the habitable zone depend on the star's size, temperature, and luminosity. Larger, hotter stars have habitable zones that are farther out and wider, while smaller, cooler stars have habitable zones that are closer in and narrower. Kepler-22, the host star of Kepler-22b, is a G-type star, slightly smaller and cooler than our Sun. Kepler-22b orbits within the habitable zone of its star, making it a prime candidate for harboring liquid water on its surface. However, the presence of liquid water is not guaranteed solely based on a planet's location within the habitable zone. Other factors, such as the planet's atmosphere, surface conditions, and potential for volcanic activity, also play a significant role. Section 4, a temperate embrace. Estimating the surface temperature of an exoplanet like Kepler-22b is a complex task that involves considering factors such as the star's luminosity, the planet's distance from its star, and the planet's potential atmosphere. Based on Kepler-22b's orbital distance and the luminosity of its host star, scientists have estimated its equilibrium temperature. The temperature it would have without an atmosphere to be around -11 degrees Celsius or 12 degrees Fahrenheit. However, the presence of an atmosphere could significantly alter this temperature. A thick atmosphere could trap heat through the greenhouse effect, raising the surface temperature to levels suitable for liquid water. Conversely, a thin or non-existent atmosphere could result in a runaway greenhouse effect, similar to what we see on Venus, making the planet inhospitable to life as we know it. Section 5. Unveiling the mysteries. While Kepler-22b's size, orbit and location within its star's habitable zone make it a fascinating and potentially habitable world, much about this distant planet remains unknown. One of the biggest mysteries is the composition and thickness of its atmosphere, a crucial factor in determining its surface temperature and potential for harboring life. Current telescopes and observational techniques are not yet powerful enough to analyze the atmosphere of Kepler-22b directly. However, future telescopes, such as the James Webb Space Telescope, hold the promise of being able to detect the chemical signatures of exoplanet atmospheres, providing invaluable insights into their composition and habitability. Another mystery surrounding Kepler-22b is the nature of its surface. Is it a rocky planet like Earth, or is it a water world completely covered in a vast ocean? Could it have continents and islands, or is it a barren wasteland? These questions continue to intrigue scientists and fuel our imagination as we strive to learn more about this distant and enigmatic world. Section 1. Atmospheric whispers. Imagine trying to decipher a whisper from across a crowded room. That's the challenge facing astronomers trying to study the atmosphere of Kepler-22b, a planet located hundreds of light years away. Despite the immense distance, scientists are developing ingenious techniques to tease out information about this distant world's atmospheric composition. One promising approach is called transit spectroscopy. As Kepler-22b transits its host star, a tiny fraction of the starlight passes through its atmosphere before reaching Earth. Different molecules in the atmosphere absorb specific wavelengths of light, leaving telltale fingerprints in the star's spectrum. By carefully analyzing the spectrum of light that passes through Kepler-22b's atmosphere during a transit, astronomers can identify the presence of certain molecules such as water vapor, methane and carbon dioxide. These molecules are of particular interest because they can indicate the presence of a planet's atmosphere and provide clues about its surface conditions. Section 2. The greenhouse effect. The greenhouse effect, a natural process that regulates a planet's temperature, plays a crucial role in determining whether a planet can support liquid water on its surface. Certain gases in the atmosphere, such as carbon dioxide, water vapor and methane, trap heat from the sun, preventing it from escaping back into space. This trapped heat warms the planet's surface, making it warmer than it would be otherwise. On Earth, the greenhouse effect is essential for maintaining a habitable climate. Without it, our planet would be a frozen wasteland. However, too much of a good thing can be detrimental. A runaway greenhouse effect, as seen on Venus, occurs when the atmosphere traps too much heat, leading to a dramatic increase in surface temperature. Understanding the balance of greenhouse gases in Kepler-22b's atmosphere is crucial for determining whether it has a temperate climate suitable for life. The presence of liquid water is considered one of the most essential ingredients for life as we know it. Water acts as a solvent, facilitating chemical reactions necessary for life's processes. It also plays a vital role in transporting nutrients and regulating temperature. Kepler-22b's location within its star's habitable zone makes it a promising candidate for harboring liquid water on its surface. However, the presence of water is not guaranteed solely based on orbital distance. The planet's atmosphere and surface conditions also play a significant role. If Kepler-22b has a thick atmosphere with a significant greenhouse effect, its surface temperature could be warm enough to support liquid water, potentially even vast oceans. However, if its atmosphere is too thin or non-existent, the planet's surface may be too cold for liquid water, and any water present would likely be frozen as ice. While the presence of liquid water is a crucial ingredient for life as we know it, it is not the only factor to consider. Life also requires a source of energy, a stable environment, and a complex chemistry that allows for the formation of organic molecules. Kepler-22b orbits a star similar to our Sun, providing a potential source of energy for life. However, the planet's stability and chemical composition remain unknown. Further observations are needed to determine if Kepler-22b possesses the necessary ingredients for life to arise and thrive. Scientists are particularly interested in detecting the presence of organic molecules such as amino acids and nucleotides, which are the building blocks of proteins and DNA, respectively. These molecules are essential for life as we know it, and their presence on Kepler-22b would be a significant indication of its potential habitability. The search for life beyond Earth is one of the most profound and challenging endeavors in modern science. While we have yet to find definitive evidence of extraterrestrial life, the discovery of exoplanets like Kepler-22b has fueled our imagination and spurred the development of new technologies and techniques to aid in our quest. One promising avenue of research is the search for biosignatures, which are chemical or physical markers that indicate the presence of past or present life. These markers can include the presence of certain gases in a planet's atmosphere, such as oxygen, methane, and ozone, which are produced by living organisms. Future telescopes, such as the James Webb Space Telescope and the Extremely Large Telescope, will have the sensitivity and resolution to detect these faint biosignatures in the atmospheres of exoplanets. These observations will provide invaluable insights into the potential for life beyond Earth and may one day answer the age-old question, are we alone in the universe? Gazing across the vast cosmic gulf at Kepler-22b, one can't help but draw comparisons to our own Earth. Both planets orbit stars of similar size and temperature. Both reside within their star's habitable zone, that Goldilocks region, where conditions might be just right for liquid water to exist on a planet's surface. But how deep do these similarities run? In terms of size, Kepler-22b is a super-Earth, boasting a radius about 2.4 times larger than our planets. Imagine a world with broader continents, vaster oceans, and towering mountains dwarfing even Mount Everest. However, size isn't everything. Kepler-22b's mass remains uncertain, estimated to fall somewhere between Earth's and Neptune's. This mass difference hints at a potentially different composition, perhaps a world rich in water or with a denser, more massive core than our own. Even with these size and mass discrepancies, the possibility of a planet sharing some fundamental similarities with Earth so far away sparks the imagination. Are there sunsets over Kepler-22b's alien landscapes? Does rain fall from its skies? These questions, while unanswered, drive our curiosity and push the boundaries of scientific inquiry. Earth and Kepler-22b both reside in habitable zones, but their orbits differ. Earth orbits the Sun in a circular path, taking 365.25 days. Kepler-22b completes its orbit in 290 days, possibly in an elliptical path. This could lead to extreme seasonal changes impacting potential life. Earth, our pale blue dot, stands as the only known haven for life in the universe. What makes our planet so special? A cradle for life amidst the cosmic void. Liquid water flows freely across Earth's surface, essential for life. Our distance from the Sun and atmosphere maintain a stable climate. Earth's magnetic field shields us from harmful solar radiation. Kepler-22b, while intriguing, remains shrouded in mystery. While Kepler-22b's potential for life remains an open question, its discovery has already taught us valuable lessons about planetary formation and the diversity of worlds beyond our solar system. The sheer abundance of super-Earths like Kepler-22b, discovered by Kepler and other telescopes, has challenged our previous assumptions about planetary systems. It seems that our own solar system, with its lack of a super-Earth, might be the outlier, not the norm. This realization has profound implications for our understanding of how planets form and evolve. Kepler-22b's larger size and potentially different composition could provide clues about the processes that govern the formation of planets in the habitable zones of other stars. Furthermore, studying Kepler-22b's atmosphere, once we have the technological capabilities, could shed light on the role of atmospheric composition in planetary habitability. By comparing its atmospheric makeup to that of other exoplanets, including those less hospitable to life, we can gain a deeper understanding of the delicate balance of gases necessary for a planet to support a thriving biosphere. The discovery of Kepler-22b, while just one data point in the vast cosmic census, has opened our eyes to a universe teeming with possibilities. If a planet bearing some resemblance to Earth can exist hundreds of light-years away, orbiting a star not unlike our Sun, how many other Earth-like worlds might be scattered across the Milky Way? The Kepler mission, despite its technological limitations, revealed that planets are the rule, not the exception, in our galaxy. With billions upon billions of stars in the Milky Way alone, the potential number of Earth-like planets is staggering. The universe, it seems, is not a barren wasteland, but rather a garden, teeming with worlds yet to be explored. Kepler-22b, whether a water world, a rocky super-Earth, or something even more exotic, serves as a powerful reminder that we are not alone in our quest to understand our place in the cosmos. The search for life beyond Earth is just beginning, and with each new discovery, each tantalizing clue, we inch closer to answering one of humanity's oldest and most profound questions. Are we alone? Kepler-22b, a celestial whisper from across the cosmic void, has captured our imagination. This super-Earth orbiting a sun-like star redefines our understanding of the universe. Its discovery yields profound insights into planetary systems and the search for life. Kepler-22b is significantly larger than Earth, with a radius 2.4 times greater. Its swift 290-day year hints at dynamic seasonal variations. Located in the habitable zone, it fuels hope for liquid water. Kepler-22b's discovery is a victory for human ingenuity. It reminds us that our solar system is just one of many in the Milky Way. Section 2, Beyond Kepler, the quest continues. The Kepler Space Telescope's legacy inspires new missions to unravel exoplanet mysteries. The James Webb Space Telescope will revolutionize our view of the universe. Its instruments will study exoplanet atmospheres in detail. Imagine detecting biosignature gases, a hint we are not alone. Ground-based telescopes with advanced optics study exoplanets precisely. Together they reveal exoplanetary systems and their potential for life. Section 3. The cosmic horizon beckons. The implications of finding another Earth-like planet, a world teeming with life, are profound and far-reaching. Such a discovery would forever alter our place in the cosmic order, challenging our assumptions about the uniqueness of life and our place in the universe. It would ignite a firestorm of scientific inquiry, philosophical debate, and perhaps even societal change. Imagine the possibilities. Studying alien life forms, understanding their biology, their evolution, their culture. Imagine the technological advancements that might arise from such a discovery, the new energy sources, medical breakthroughs, and materials inspired by extraterrestrial life. The potential benefits, both tangible and intangible, are staggering. But beyond the practical implications, finding another Earth would touch upon something deeper, something fundamental to the human spirit. It would reaffirm our sense of wonder, our innate curiosity about the universe and our place within it. It would remind us that we are part of something much grander than ourselves, a cosmic story billions of years in the making. Section 4. A universe of wonder, a future of discovery. The universe, as we are beginning to understand it, is a place of astonishing diversity, a cosmic tapestry woven from billions upon billions of stars, planets, and galaxies. Each new discovery, from the smallest subatomic particle to the largest superclusters of galaxies, fills us with awe and wonder, reminding us of the boundless possibilities that lie hidden within the fabric of space-time. Kepler-22b, a distant world orbiting a distant star, is but one small piece of this grand cosmic puzzle. Yet its discovery has ignited our imaginations, fueling our desire to explore the cosmos, to seek out other worlds and to answer the age-old question, are we alone? The journey ahead will be long and challenging, but the rewards, both scientific and philosophical, will be immeasurable. We stand on the precipice of a new era of exploration, an era marked by unprecedented technological advancements and an unquenchable thirst for knowledge. The cosmos beckons, and we as a species are ready to answer its call. Section 5. Are we alone? The search continues. The search for life beyond Earth reflects our deepest hopes and fears, uniting us in a shared sense of wonder. Kepler-22b symbolizes this quest, reminding us of the universe's possibilities. The search continues, inching closer to unraveling life's greatest mystery.